Hi, my name is Dan McDonald. I lead the synthetic geometry team here at Wolfram, and my talk is about our new functionality coming into version 12.0 experimental. I'll discuss our main functions, which include geometric scene for describing coordinate-free scenes in plane geometry, random instance for creating a random drawing of a described scene, and find geometric conjectures for creating conjectures based on those drawings. Also preview some future functionality for making synthetic proofs about those scenes. Hello, Champagne. Okay, so my name's Dan McDonald, and I lead the synthetic geometry team here at Wolfram, and I'll be talking about our project, Automated Drawings, Conjectures, and Proofs in Planar Geometry using the Wolfram language. At least the first part of this is similar to a talk I gave in Portugal a couple months ago, so if you were at that one, you can nap for a little while. Okay, so just an overview of our project. Hopefully you can read that. We kind of have, I guess, four phases of our workflow. The fourth one is not really showing. Our three main functions making it into version 12, experimental at least, are geometric scene, which is a wrapper used for describing, symbolically describing coordinate-free scenes in plane geometry, and I'll show you what I mean by that later. Random instance, which presumably will become a more general function, but for us, we will apply it to geometric scene to create randomized instances of those described scenes. Find geometric conjectures will use those randomized instances and the concrete coordinates they return to make conjectures about the original abstract scene. And it's not letting me scroll down. How do I, there we go, oops. It's the 75 at least. And then finally, find geometric proof will not be in version 12.0, but it's got some working code, and that will be for actually finding human readable proofs of theorems described in our scene language. So let's show what we've got. So let's go back to 100. So we always start these talks with Thales theorems because, as we say, Thales never fails. I used that last year. No one laughed then either. So Thales theorem says, let A, B, and C be distinct points on a circle where the line AC is a diameter. So here, this picture we got off the internet, I guess, doesn't have A, B, and C. Imagine A here, C here, and then B is one of these points here. Then the angle ABC is a right angle. So if we want to describe this, we have geometric scene. We list the points. You don't have to list them as strings, but this is not a scope. Geometric scene does not scope, so it's safe to do it that way. Circle through will be a new graphics function. I'm not sure when that will actually be working, but circle through ABC centered at a point at the O, and then we have a triangle ABC, and O is the midpoint of A and C. So notice we didn't say anything about the conclusion. And then if we run the code, we get an instance of this scene. This is from random instance. So notice this is random instance. So if we run it again, we should get something else. If we want multiple, say 5 versions, it'll take a little longer. We can get a list of different results, but let's go back to 1. Okay, and notice that there are multiple ways of describing the hypotheses of Thales' theorem. So let's try another way. So let's say the circumcenter of triangle ABC is also the midpoint of AC. So we should be able to get a drawing here, and the drawing looks a little different, but it still fits the theorem. So in case you're curious, this is not actually a graphics object we're returning. This is, it formats as graphics, but the head will still be geometric scene, except we've given concrete values to the points. And those concrete values are important if we run fine geometric conjectures, because fine geometric conjectures uses the concrete coordinates to see if there's anything interesting to say about the scene. So here, we run it, we get geometric assertion. This is another new function that'll work inside geometric scene of line A, B, and C, B are perpendicular, which is the same thing as saying that this planar angle, which Charles has introduced in the more general geometry framework, equals 90 degrees. So we've got the conclusion, and also if we run it on the second picture, it works there too. So let's close that. Let's see, so here's another example. So I think Charles used this in his talk if you were there. Pappus's Hexagon Theorem. Notice here we have a random seeding option, which is helpful for talks when you don't trust your software a lot, because here we notice it puts out a good picture, but I knew it would because with the random seeding option, you get the same thing every time. If I take this away, we might see why plane geometry is like people in that we can't all be winners. See, sometimes you get a degenerate scene, so hopefully if you run it enough times, you'll get something good again. There we go. So it's an imperfect science. It doesn't always give what you want. And if we look for the conclusions on this guy, we see that our top conclusion is geometric assertion of z, y, x are collinear, which is this red line here, and which in fact was the conclusion of Pappus's Hexagon Theorem. So good job, Pappus. Castaneta's theorem, that was the one Stephen did in his talk, so I'll skip ahead to our preview of fine geometric proof. So this is not going to be available in 12.0 at least, so I just have some example output down here. So what is the measure of angle ZUV in this diagram I'm going to generate? There we go. And if we run our conjecture code just for completeness, we'll see that it finds that VZ is 150 degrees. And if we want an automated proof, I don't have code to actually run on this, but at some point this will be available. You'll return a proof object, and then you'll be able to format it where you'll have facts and reasoning, and at the bottom you should get what you want. So since XZU are on a line, ZUV is just XUV by another name, which is 150 degrees. And that should follow from these things up here. Okay. Next. Okay, so some other things we can do. So let's look at Finsler-Heidegger theorem. So suppose A, B, C, D, and A, B prime, C prime, D prime are two squares with a common vertex A, something, 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 and the conclusion is this quadrilateral QRST must be a square as well. So let's create a scene description based on those hypotheses. So we've got two polygons. They're squares, so we say geometric assertion regular. We have Q, S, R, and T are these various midpoints. And then this polygon QRST, I'm not making any assertions about it, but we're just going to draw it to see what it looks like. And according to Finsler-Heidegger theorem, this polygon QRST must be a square. So let's run this. And what do we get? It is not a square. That looks like a non-square parallelogram. So, if we, in fact, try to find conjectures about this being a square, we don't find anything. So what went wrong? We need to add the assumption that the two original squares are both counterclockwise. So this is something that I think we got this from Math World, was not present in this original problem description. So it's something where later on, if you're doing automated reasoning about theorems like this, computers don't make assumptions. So this is a tool for seeing if you are making any implicit assumptions that you're not aware of. So if we actually run it with this additional assertion that P1 and P2 have the same orientation, we see that, in fact, we do get a square. So Finsler and Heidegger, who I looked up, are both dead, but now they can rest in peace because their theorem lives on. And our conjecture code does find the conclusion. Not yet. I believe so. Although I was mostly looking over my talk during that talk. Yeah. Okay, so another application for the drawer is in Polygon Dissections. And so I don't know if Ed Peg's in the audience, but he found these. So a perfect dissection of a polygon is a decomposition of the polygon into internally disjoint polygons, finite number more than one, that are mutually similar but pairwise incongruent. So there's this area of mathematics where you describe a dissection and see if it's possible to actually achieve it. So here's one. Notice these numbers are just labelings for the lines, not lengths. So we want to give a dissection of a triangle into 1, 2, 3, 4, 5, 6 similar triangles. And if we run this one can take a while, except if you pick the right seed, it does not. And in fact, we get this. We get the construction that took us humans so long to come up with up there. And we can do this again with this dissection here. So let's see if ours looks similar to theirs. And it does. So also notice that if you name, so notice you can use style around any of your willy-nilly around any of your graphics primitives, and if you give it a name, you'll get a tooltip. Okay, so that was kind of what's going on inside of geometric scene. We found that we needed some more functionality to kind of fully be able to fully express the breadth of planar geometry, and some of this functionality is going to be able to live outside of geometric scene. Triangle construct is one, and so these are the heads in blue, and the strings, if they're here, are specifications. So we have some somewhat obscure things: medial triangle, anti-medial triangle. You can look on. So triangle construct will return something that you can put directly in graphics. Triangle measurement will return a scalar value. Triangle center is similar to triangle construct, except it only works. It only returns lists of coordinates for points. So this list of strings will be a subset of this list of strings. We have midpoint, which doesn't take any specifications. If you're at Charles's talk, he's implemented planar angle and polygon angle. And we've also implemented angle bisector and perpendicular bisector. So let's see some of these things in action. Right, so if we look at a 9-point circle, we'll show you why it's called a 9-point circle. So let's run these things. Right, so it's a 9-point circle is defined based on a triangle, and so its center is one of our triangle centers, and the vast majority of these functions and their specifications work on abstract input. So we've got a 9-point center, a 9-point radius, and that should be enough to give us a 9-point circle. And if it works on abstract input, it should work on concrete input. So if we run this here, we see why it's called a 9-point circle. So we've got this triangle, we've got 3 feet of the triangle, an orthocenter, 3 midpoints between the orthocenter and the vertices of the triangle, 3 midpoints of the triangle, and that gives us a total of 9 points that this 9-point circle happens to go through. If we look at angles and bisectors, we can run this. We've got angle bisectors, which will be this guy, exterior angle bisector, which will be this guy at the same vertex, perpendicular bisectors, which would be this guy here. So these bisectors return infinite lines. If you're at Charles's talk, you saw the stuff we can do with angles now. So planar angle. So this is a planar angle. So this would be at the point 2, 0, which would be over here. If you don't add additional specification, then it just gives the angle between 0 and pi. But you can also give the specification for orientation. So clockwise will be the same thing, pi over 4. Counterclockwise will be going the other way, 7 pi over 4. We also have polygon angle, where you give it a polygon and you can specify based on a vertex or an index of a vertex. So this would be this angle over here, 63.5 degrees about. So that's the interior angle. We also can give the exterior angle, which is if you extend one of these sides out, or the full exterior angle, which is if you go all the way around the outside. And then I got about 30 seconds left before questions, so we'll just do some more constructions. Right, so here are An original triangle is the one in green, and then the medial triangles on the inside, anti-medial on the outside. We've got the 3 X circles of a triangle. And here we notice that one way of defining the orthocenter of a triangle is the intersection points of all the altitudes. And finally, if you've ever heard of an Euler line, it's the line that goes through several important points, not the least important of which are the centroid, the orthocenter, the circumcenter, and the 9-point center. Okay. So thanks for listening. So the rest of the synthetic geometry team, the ones who are actually here are Ian and James. Lynn Kong and Peter Brins and Michael Trott are not here. Peter is working on the prover. Lynn does the conjecture code. So we also have thanks for our test suite developers, graphics and formatting, and especially Charles and Itai have helped us out a lot because we're mostly alpha people kind of fumbling around in the dark in a mathematical world. So thank you.